have a good. Thank you, Diana, to the recording. So today, for Dr. J. Austin, and then, I will ask if Dr. Austin actually introduce himself.
Sure.
Because you were BGS for the WRS program.
Yep, I just stepped down after 3 years as the DGS for water resources. My name is Jay Austin. I'm a professor at the Large Lakes Observatory and in the Department of Physics and Astronomy here. My background originally is in oceanography. I did a PhD at MIT in Woods Hole, studying coastal oceanography. And I, like a lot of people at LLO, are bringing oceanographic technique to studying big lakes like Superior. You can't study Lake Superior the same way you'd study Lake Mendota or something like that. And so we need oceanographic vessels and oceanographic equipment in order to do stuff on these scales. This is the title of my talk, and I regret having sent this title in. This would have been a better title. This is not a data report. I'm not just here to show you a bunch of slides with data. I'm here to talk about how the Great Lakes look in the winter. What is their temperature structure in the winter? And so I'm going to convince you that that's probably something that if you're doing anything associated with lakes, there are probably more people out here from sort of an ecological or biological standpoint than a physics standpoint. But I want to convince you that understanding stratification is important. You also might say, this seems like a really sort of fundamental basic thing that surely somebody did back in the 60s. And you would be wrong. It's really, really bizarre that this sort of information isn't out here. And I'll tell you a little bit about that story as we go along. Who here is associated in one way or another with LLO? About a third of the hands. And so I'm going to take just 2 slides here really quickly so that people know. The Large Lakes Observatory is a group of faculty on campus. You can tell how old this slide is because it says geology and not EES. But a group of faculty from EES, biology, chemistry, and physics, who all have interest in the fundamental underpinnings of how large lakes around the world work. And so we're not the Lake Superior Observatory or the Great Lakes Observatory, the Large Lakes Observatory. We work on a wide variety of lakes all around the world, have a real focus on the Laurentian Great Lakes, obviously, but also, for instance, East African Rip Lakes, and really anywhere we can find interesting projects. There's a wide range of interest at LLO. But if I had to pick a common theme among all the faculty there, it would be climate, and not just modern. I do modern climate stuff. So I go out and make observations and I tell stories about how the lake is responding to climate change. But we also have people that do a lot of paleo oceanographic work where you're doing sediment core analysis and stuff like that to try to understand what the climate looked like in the past. Because in order to understand, put the future in context, we have to understand things over a much longer time scale. My work personally, I'm an observationalist. I go out on boats, I throw things in the water, I hope to get them back. I work on a wide variety of topics. The sort of first stuff I did when I moved from the oceanographic community into freshwater was looking at climate change responses. That got me really interested in winter conditions and shoulder seasons. And so I'm doing a lot of work on those sorts of things right now. Acoustics shouldn't be quite as high up on this list as it is, but I've done some passive acoustics work, trying to understand what the lake sounds like, because I haven't done it. Physical biological interaction, how the physical structure of lakes influences ecological function. And I've spent a lot of time over the last several years thinking about springtime convection in deep lakes. In addition to the work on Superior, I have a bunch of thermistors in an ultra deep lake, Lake Quesnel, in British Columbia. And as of last week, I have 2 moorings in Crater Lake in Oregon as well. In addition, the meteorology buoys that are in the western arm of Lake Superior are all operated out of my lab. So lots of fingers and lots of pies, but really the focus on understanding the physics of these large systems by making direct observation. So I'm going to just talk about what the idea of lake stratification is, why you should care, regardless of what field you're in. And then I just want to talk through what we know and what we don't know about winter stratification in the Great Lakes. To be clear, we know a fair amount about summer stratification, about summer structure in general in the Great Lakes. And there's been this realization and focus over the last maybe 5 years, including by a lot of people here at LLO, that we really need to do a better job of addressing what's going on in these lakes in the winter. And it's largely a logistic thing. It's hard you can't get out on a boat in the winter. You wouldn't want to. And so we have to look at other techniques for expanding our scope into the winter season. I'll also, this is, first of all, a couple of things. This is the first time I've given this talk, so we'll see how it goes. The other thing is I'm just finishing a paper on all of this right now. And I have a long list of co-authors from the Great Lakes Environmental Research Lab in Ann Arbor, which is the big NOAA lab that's supposed to cover the Great Lakes. I could have had them on the title slide, I suppose. So this right here, and we'll walk through this, is sort of the fundamental fact behind the fact that lakes stratify in the weird way that they do. And by lakes, let's say freshwater lakes. Very different from ocean systems where salt plays an important role. You are used to the idea that density can be a function of temperature, and that can cause a fluid to layer itself. You go into your house on a warm summer day, and upstairs is warm and downstairs is cool, and that to a large extent is because that cool air is denser and sinks, the warm air is warm and rises. Fluids like to stratify themselves such that lighter fluids sit on top of heavier fluids. You have oil and water or oil and vinegar in a jar. The light density oil sits on top of the heavy density water or vinegar or whatever. That's just a basic property of fluid stability. Lakes do the same thing above 4 degrees Celsius as you would expect from an ideal gas, in that as they get warmer over here, warmer in this direction, they get less dense. And so if we go out in the summer and we make a measurement of temperature as a function of depth, we'll see warm water sitting on top of cool water below. On the other hand, over here, below 4 degrees Celsius, that's about 39 degrees Fahrenheit, when we talk about Celsius. It does the opposite. As I warm it, it actually gets denser, which is really bizarre. And I'm not going to go into the physical chemistry of why water behaves that way. This is a real anomaly in the land of fluids in general. There are not a lot of things that have this bizarre behavior, but the most common fluid on Earth happens to have this really strange behavior. And so here are a couple profiles from a mooring in the western part of the lake. In red, we have a profile in the summer, well, actually technically the fall, I suppose, from the 22nd of September, and you see a thin layer of warm water sitting on top of cooler water below. In purple is a profile from midwinter, where you see very cold water right at the freezing point, 0, sitting on top of slightly warmer water below. The blue dashed line is the temperature of maximum density, and if you look at that very carefully, you'll see that it actually gets a tiny bit colder as we go deep in the water column. That's not really relevant to this talk, I'm just pointing that out. And then the yellow curve is one in December that actually passes through that as the lake is transitioning from its warm stratified state into its cold, inversely stratified state. Yeah, and you'll notice this red curve hugs that blue dashed line really, really precisely. Why should you care about stratification? Not a huge number of physicists in here. I care about stratification because it's fundamentally an interesting thing to study. But it also plays a huge role in determining how properties of water are mixed through the water column. And so these are two profiles. These are profiles of a whole bunch of different properties that were taken with a profiling instrument from the Blue Heron on 2 days, the 8th of May in 2019, and then the 11th of June, a little bit later that year. The temperature profile on the 8th of May has a very, very strong gradient at right around 100 meters. So we have very cold water sitting on top, right at the freezing point. No, I'm sorry, not right at the freezing point, around 1.5 degrees. And then deeper in the water column below 100, we see slightly warmer water. You should notice that the differences I'm talking about are really small, right? But they are enough to impose stability on the system such that stuff that's in the upper layer stays in the upper layer, stuff that's in the lower layer stays in the lower layer. You see here on the 11th of June, the temperature profile is pretty uniform, a few hundredths of a degree over 180 meters, so very, very small differences. Now look at properties that you as an ecologist or a biologist or a chemist might actually care about. Chlorophyll fluorescence. there's significant chlorophyll in the upper portion of the water column and none in the lower. And that's because all the sunshine is in that upper layer, and you get mixing in that upper layer, redistributing stuff, but it never mixes with the water below, which is completely devoid of chlorophyll fluorescence. Chlorophyll fluorescence is a very rough hand-wavy measure of phytoplankton abundance. Dissolved oxygen, same thing. In contact with the atmosphere, relatively high level of dissolved oxygen, slightly lower levels below. Once the water column is mixed, you can see that suddenly we have a much more uniform distribution of oxygen throughout the water column. Likewise, with colored dissolved organic matter and transmission, which is a measure of water clarity or turbidity, however you want to think of it. The point here is that how lakes stratify fundamentally influences how stuff that you might care about is distributed throughout the water. Okay. Not all lakes stratify the same way. These are attempts at coming up with classifications for whether a lake stratifies positively in the summer and negatively in the winter, or only in the summer, or only in the winter, or doesn't stratify at all, or stays stratified all year long. There are lots and lots of different things. And these two old papers, Hutchinson and Loeffler, 55, and Lewis in 83, are attempts at using things like latitude and depth and latitude and altitude and lake depth to push these lakes into little boxes, which I really dislike. And I'm going to tell you why I dislike that by the end of the talk. Latitude is important because it determines how much sunlight you're getting and how strong the annual signal is. Altitude is important because it controls to a certain extent air temperature. And lake depth is important in the Lewis categorization because of it's hard to form stratification in a lake that's too shallow. It's too easy to mix that stratification away. These are developed by people who work on small lakes. And what I'm going to show today is that you, at your hazard, try to take Lake Huron and squish it into one of these boxes. It just doesn't work that way. You can also tell that they were probably some sort of ecologist because they'd like to make keys, so that you can ask a bunch of questions and then determine which one of these boxes you push your lake into. Okay, so what data do we have available to us to study how these lakes behave in the winter? And I'm gonna focus entirely on the Laurentian Great Lakes here. And so there are two organizations that have collected basically all of the publicly available lake temperature data that I can find, subsurface, where there is good winter coverage. Those two labs are the Large Lakes Observatory, myself primarily, but also Sam Kelly, Joe Verney, a couple of other people have contributed to a very long time series collected at WM, which stands for Western North. I had a big project back 2008 to 2012 to look at winter structure across the lake. We occupied far western, western, northern, central, eastern, far eastern, and southern mooring. Very creative names. Sam Kelly had a big project a few years ago looking to determine waves. He occupied GM1, Grand Marais 1, and Grand Marais 2 for several years. And one of my weather buoys is here in the far western arm, and we tend to throw a little baby mooring in over the winter so that we get a whole year of coverage. The buoys we have out have to be removed. Surface buoys have to be removed because they're not ice hardened, and they don't get enough solar panel power to last through the summer anyway. The Great Lakes Environmental Research Laboratory, GLERL, has that western site. There's been something there since about 2005. GLERL has had a site here in southern Michigan since the mid-90s, making it the longest time series anywhere in the Great Lakes. They added a Superior station in 2018, a Huron station in, I don't remember the date, but those ones are not quite as long. The point is we do actually have multi-year time series in 3 of these lakes. For Lake Erie, which is surrounded by major population centers, I could find 2 winters worth of temperature data, both in 2004 and 2005, as part of the international field year for Lake Erie. And we're going to work with those 2 data sets. Notice that Ontario over there has no dots on it. As of last Wednesday, I found Canadian colleague in Toronto, that has some stuff. I'm not gonna include any of that Ontario data because I only discovered it last week. He only has 2 winters worth. So that tells you something about the state of temperatures, like literally the easiest thing to measure, of anything you will ever measure in a lake. And this is how little data, and temperature plays a huge role in controlling how lakes work. And this is how much data we have. That's to me, a real mismatch. How do we measure this? This is a simple schematic of a mooring. This is from our western mooring. It's 185 meters deep. You can see the blue is the surface. The Coast Guard keeps us out of the top 10 meters of the water column because they don't want boats hitting our platforms, nor do I want boats hitting my platforms. So I'm perfectly happy to lose that top 10 meters. We have a heavy anchor. We buy big concrete bunker blocks. And then we have a piece of steel cable that goes up to a subsurface float in yellow. On that cable, we attach thermistors. Here's one. I'll show. Are they seeing me at all or no?
You need to turn on the beam.
Oh, no, I don't, because I'm sharing my screen. So I really need to work this out. Yeah, that might, just leave it there. It's fine.
Yeah.
So this is a temperature sensor. We call them thermistors. I'm going to pass it around here in a second. There's a little sting here, which is the bit that you would put under your tongue, as it were. That's the thing that's actually doing the sensing. And then inside here, there's a AA battery. There's a little computer, a little place to plug your USB cord in. This can record temperature accurate to about 2 millikelvin once every 5 seconds for a year on a single AA battery. They're about $700 a piece, which is not a whole lot of money compared to, say, a day on the blue heron. We would have maybe a dozen of those throughout the water column so that we can look at temperature at a bunch of different depths. Starting in 2021, from 2021 to 2023, we had a mooring at Western that had 90 of these in the vertical, and you get to start to ask all kinds of really cool questions when you have super high resolution in the vertical, and also sampling really quickly. Okay, so the data we're going to look at are from platforms like this, where we're measuring temperature at a bunch of depths. Here is data from our Western mooring for 2 years, and I'll walk you through this. The individual curves are temperatures from different thermistors. The shallowest thermistor I've marked in red, so you can see here, and the deepest one in blue. So here in the summer of 2013, we have warm water sitting on top of cold water. We have a transitional period right here in the fall. Eventually, winter stratification forms where we have cold water sitting on top of warm water, as I showed in that profile earlier. Then a spring transition, then the next summer, then a fall transition, then the next winter. The gray curves right here are ice cover at that location. And so we use satellite data to determine the amount of ice cover in the vicinity of our mooring. We use satellite remote sense data for that. And so you're going to see a bunch of plots that look like this. I've spent a bunch of time trying to find examples of winter temperature data in the literature. There are not a lot. Here's Ned Smith in 73 in Lake Superior. This is 10-meter data. This is 200-meter data. Unfortunately, his deep temperature sensor conked out after just a few months. If you plot those on top of each other, not easy to see. You can see summer stratification here, this mixed period, and then it just starts to form proper winter stratification when this sensor fails and we don't get any data. This is Lake Huron. This panel and this panel are the same platform. You can see relatively well mixed here, but then in March, you start to form just a little bit of stratification at that particular site. Most of what you'll see in the literature is stuff like this, where here's Schertzer trying to determine heat content in Lake Erie. So taking a look, basically average temperature through the water column. But you notice that there's nothing for January, February, March. Here, Bennett in 78. a couple points here in January, but really nothing there. And you just sort of have to guess as to what's going on as far as the range of temperatures through the water column. The best characterization of winter stratification that I am aware of, this is going to seem a little conceited when you see the next slide, was done by a WRS student, Dan Tietze, who's now one of the lead modelers at GLERL out in Ann Arbor. And he took a bunch of the data that we collected and did a really nice descriptive job looking at a cold winter in 2009 and a warm winter and doing a lot of compare and contrast. These are 3 different sites across Lake Superior. And you see here this water very close to freezing at the surface in all 3 sites. And then here in a warm year, the temperature only getting down to 1.5 or 2 degrees or even warmer at those other sites. He followed that up in 2016 with a descriptive paper covering the polar vortex winter. People remember that. It was just brutally cold all winter. The lake reflected that. Lake responded very, very differently in that winter. And so he did a paper in 2016 doing things like estimating ice thickness and drift, ice keeling, where shaped plates of ice come together, form these gigantic keels, and some novel acoustic observations. And so there's really not a whole lot out there past these papers of Dan's, as it were. My name is on there because I paid for it, not because I did a lot of the work. He's a really, really smart guy. I want to talk about 2 measures of lake stratification. So we have to take these big time series, tons of data, and boil them down to relatively small amounts of data that we can ingest. And I'm going to propose 2 that I'm going to use here. Heat content, I'm going to define these in a second, and stability, which is often referred to as the Schmidt stability index. I'll just refer to it as stability. Heat content is the amount of heat that I have to put in thermal energy to warm the energy from some base state, and I'm going to use the temperature of maximum density for that, to its current state. So if the water is warmer than the temperature of maximum density, I have to put heat into the system. So here in the right panel, it turns out that that heat content is proportional to the area between those 2 curves. So that basically the gray area on the right. If I'm in the winter and the temperature is below the temperature of maximum density, we still compute the area of that region, but we put a minus sign out in front. And so if the heat is greater than the temperature of if the heat is greater than 0 relative to the temperature of maximum density, we know that we have summer stratification or summer temperatures above the temperature of maximum density. And below that, below 0, the temperature profile is below the temperature of maximum density. Stability index is a little harder to understand. So don't worry about any of the math up here. I'm just putting these up here to demonstrate that I can take a bunch of thermistors on a cable and compute a single number that tells me about the condition of the temperature stratification at a given time. Really what you should think of this as just a measure of the strength of the stratification. From a physics standpoint, it's the amount of energy necessary to take the water column from its stratified state and mix it to an unstratified state. You actually have to put energy into the system to do that. And this is a measure of that energy. Don't worry about the details. The point is, the bigger this number, the more stratified, in some sense, the water column is. An unstratified water column has a stability of 0. And that number is never negative. Okay, now I'm going to walk through a few lakes. Okay, yeah, here's the map again, apparently. Here is Lake Superior in a cold, a moderate, and a warm year. And so you can see in the winter, we get this long period of close to 0 degree water at the surface, warmer water below. You can see the gray bar, ice forms. You can see the stability grow and then decrease, heat content decrease. It levels out here because ice forms and you cut off the exchange of heat between the atmosphere and the lake below. And so it's pretty flat through here, even though it's just bone cold at this time. You don't get a lot of heat loss. Here, we see less stability, higher levels of heat content. And finally, in the very mild winter of 2012, it forms stratification, certainly, but it forms no ice. It doesn't get anywhere close to 0 degrees. You see only a little bit of ice in this 2021 column. In contrast, this is a shallow site. This is my far western, or the western buoy, the site in the far western part of Lake Superior, relatively shallow, about 50 meters deep. And you can see that it cools off isothermally. The entire water column cools off, gets to the freezing point, and then the game's over. It just stays at the freezing point. I'm not sure why this is like. In 2019, 2020, sort of furtive attempts at forming stratification. And then in 23, 24, this last winter, which we all acknowledge is a very, very warm winter, it really only gets down to about 2 or 1.5 degrees before it starts forming up again. Little bits of ice do get blown in every now and then. You see little sporadic gray bars up there. So that's ice that's drifting into the region and being remotely sensed. Lake Michigan, the cold year of 95, 96, we get a little bit of stratification, not a whole lot. Stability is relatively weak compared to what we saw on Superior. But then even in a moderate year, 2005 to 2006, it barely gets below the temperature of maximum density before it warms. And in the very warm winter of 2012, it doesn't even reach the temperature of maximum density. It starts cooling off and it's like, nope, time to for summer to start again. And it starts to re-stratify there as early as March, which is really remarkable. Lake Huron, polar vortex year, it's very similar to Superior. Lots of stability, very, very low heat contents. Moderate year in Superior, a little bit of stratification. And then in the winter of 2021, no stratification at all. And so how do you fit that into one of Hutchinson and Loeffler's boxes, right? It's displaying very, very different behavior, and as did Michigan. I will caveat Lake Michigan really quickly in that their mooring during the very cold winters of 2014 to 2015 failed. And so we have no data in the upper portion of the water column for those 2 years, which is an absolute shame because those would be the really interesting years for us to have data from. Okay, and Lake Erie, very much like mine, my very shallow sites, cools off to 0, boom, warms back up. This site's a little bit deeper, so it cools off a little more slowly. But again, essentially no stratification. This curve right here is basically 0, a little blip there maybe. And you can see the heat content leveling off because it can't cool off anymore once it reaches the freezing. And so this to me is amazing. We have these 4 lakes that are all relatively, in some sense, close to each other, that all behave in very different ways. And so we can start to dig down on this a bit. The upper 3 are heat content in Superior, my site at Western, and then Glural sites in Michigan and Huron. The bottom row is stability. In all of the years that we record data in Superior, notice that this curve gets above 0. Not a whole lot in some years and a whole lot in others, but the point is it's always greater than 0 here in the middle of March. Lake Superior at this site, always, every year that we have data for, forms stratification. I could make this plot for the other, 7 or 8 deep water moorings, and all of them would look like this. In Michigan, basically 0 throughout the entire winter. A couple of little attempts to form stratification at times, but by and large does not form stratification. And then Huron, several years where there's nothing, and then several years where there is. And so those 3 lakes all display some sort of different behavior. Doing an interlake comparison in Superior, in 2011 and 2012, we had 7 moorings, 1, 2, 3, 4, 5, 6, 7, 8 moorings, deployed all at the same time. Probably the biggest in 2 winters across the Great Lakes ever, as far as having instrumentation in the water. 5 of these sites look very, very similar in this year and in this year. 2 sites that I've circled in red, both deep sites in the eastern part of the lake, lose considerably more heat in both years. And then this dashed curve is our meteorology site in the far portion of the lake that just can't cool off as much as the other sites because it's shallow. There are 5 years where LLO's Western and Glural's Superior mooring were in the lake at the same time. And you can see that a cold year in one year, a cold year in the western part of the lake is a cold year in the eastern part. This is minimum heat content on both of these axes. And a warm year at one side is a warm year at the other side. So the lake is responding in some relatively coherent fashion, which is nice to know. We can do the same except do intra-lake comparisons. So I'm going to compare my superior western site to Glurals, Michigan in this panel and Huron in the other panel. And the relationships, maybe unsurprisingly, are nowhere near as clean. Michigan is always warmer than Superior for its minimum heat content, which is not a great surprise. And then the Huron site, a little more coherence, cold years are cold years, warm years are warm years, but in both of these cases, I'd be really nervous about like fitting a line or something through that data. It's really messy. The other caveat that I forgot about with Lake Michigan, let me back up for a second here, is that in Michigan, this site is really far south in a lake that's oriented northeast or north-south. There's a deep basin up here. If I was a betting guy, I would bet a shiny quarter that in cold years, stratification does form in the northern portion of the lake, but we don't have the data to show that that's in fact the case. And so we are constrained by the fact that we have that one southern site. Happens to be offshore from where Glural has their field station. Okay. What drives heat content? Why are some years warm, have high heat content? Why do some years have low heat content? Maybe not a great surprise. It's very strongly linked to air temperature. And so this is Huron data. December, January, February, average air temperature on the x-axis, and then minimum heat content on the y-axis. And here I obviously was brave enough to run a fit here. And so you see that something like 65% of the variability from year to year is simply linked to air temperatures. These are these very big complex systems with lots of really interesting mechanisms that cause heat to be exchanged. But it boils down to whether it was a warm winter or a cold winter, as to whether it's stratified, or as to what the minimum heat content is. Okay. I'm talking fast. Let's realize. So why does stratification form in some lakes and not in others? In the case of Lake Huron, in some years, but not in others. And this is a very empirical take on this, and I have to say that I'm not satisfied with my answer so far, and I'll tell you why in a second. If I look at, so this is a measure of stability, stratification stability, and this is a measure of the minimum heat content. And you can see that if you are warmer at minimum of more than about -1 is a gigajoule per square meter, it's a measure of the heat content. If you're warmer than that, either at any of Glural's moorings or at my shallow, the square boxes at shallow moorings, you essentially get this zero stability means you get no stratification. On the other hand, if you're on this side of the curve, you start to see this data. If I take more heat out, I get stronger and stronger stratification. So this right here seems to be a threshold value. If I take more than a gigajoule per square meter of heat out of the lake, I'm probably going to form stratification. I find that a little unsatisfying that I can't tell you why that number is a gigajoule instead of 10 or a half or something like that. So that's stuff that we're still working on. The point is, all of these points over here are, each one of these points is a different year. In the case of the Glural data, in a different lake. All of these points right here are points where the lake simply did not cool off enough, and hence did not form stratification. So Erie, because it's so shallow, but Michigan, because it just never loses a whole lot of heat. Whereas the red dots here are Superior, they lose significant amounts of heat and cool off. And then the blue dots are Huron, you can see them on both sides of the curve. Years where it stratifies, years where it doesn't. I would love to know, to be able to write down an equation that told me why this in particular is that threshold. If you look at vertical stratification across the Great Lakes, this is the Superior Western site, and then Glarus, Michigan, and Huron sites. These are profiles on the 15th of March in a whole bunch of different years. You can see sort of a commonality here of strong stratification in sort of the 60 to 100 meter region, although there's a little bit of stratification in the water column. Huron, you can see a handful of years that do stratify, a handful of years that do not. And then Michigan, by and large, are all relatively vertical. Many years here, you can see on the right side of that temperature of maximum density, suggesting that we're not forming negative stratification in those years. One nifty thing we can do with this threshold value is determine how deep a lake has to be in order for it to form stratification. If a lake is shallow, I can only take so much heat out of it before it reaches the freezing point, at which point ice is going to form and stratification will never. So I can scale that heat content against the temperature difference between the temperature of maximum density and the freezing point. So don't worry again too much about this, about the form here. The point is we can use math to figure this out. And what we get is a critical depth of about 60 meters. So what I'm saying is that I would expect in the sort of meteorological environment of the Great Lakes, that locations shallower than 60 meters, give or take, regardless of the meteorological conditions above them, will not form stratification because they'll reach the freezing point first. If a point is deeper than that, as long as it loses enough heat, it will form stratification. If you're Lake Michigan, you're nice and deep, but you're not losing enough heat to start to form stratification. So it acts as a nice sort of threshold value and starts to give us a clue as to what deep structure might look like away from all the points that we actually have data at. So I probably shouldn't have put this in, but the idea here is I want to know, well, I'm totally ignoring the fact that you still have to take heat out of the system in order to form ice, right? We put ice cubes in the freezer, certain amount of water in the freezer, and a certain amount of heat has to be taken out of that water to the latent heat diffusion and stuff like that. And it turns out that the amount of heat necessary to form ice of thicknesses, we know very, very little about how thick ice is on the Great Lakes. It's a really, really hard thing to measure. But with reasonable estimates of ice thicknesses, the amount of heat necessary to form that ice is much, much smaller than the amount of heat lost by the water column below. And so unless you're in, a shallow coastal region, or you're in Western Lake Erie, where they get loads of ice, and it's really, really shallow, you probably don't have to worry about ice, the amount of heat being put into causing water to turn into ice. Okay, a summary and then a quick conclusion. And I love the fact that we have these 4 lakes and none of them look like the others, right? That's really, really cool. In Superior, does it stratify? Yes, as long as the water is sufficiently deep. We think maybe 60 meters is a hand-wavy cutoff for that. There's a lot of interannual variability in the amount of ice that forms. Michigan doesn't form, at least for the data that we have. Again, southern site, missing those 2 really interesting years. So let's just say no. Does ice form? No, doesn't form in the western basin of Lake Michigan. Huron stratification, back and forth, depending on whether it's a cold or a warm year. Ice forms in some years. Erie, stratification doesn't form, but ice does pretty reliably form in Lake Erie. And so here are these 4 lakes, again, all relatively geographically, quote unquote, close to each other, that have these 4 very disparate behaviors when it comes to winter physics. Okay. So conclusion and then questions. So there's a tremendous variability in winter structure, temperature structure between lakes. Huron sits at a boundary between these stratification regimes, which means that the how the ecology functions in the winter in Lake Huron is going to be fundamentally different between a cold year and a warm year. Stratification structure may depend on depth, but it still will have remarkable variability from year to year. Within Michigan or within Superior, Huron obviously is the real standout there. And then ice probably doesn't play an important part of the heat budget of lakes, except in shallow coastal zones and western Lake Erie. Although ice does play a significant role in forming a cap and trapping heat in some sense, or cutting off the exchange between the atmosphere and the lake below. So, okay, that was a whirlwind. I hope some of that made some sense. It's again, this information gap, this knowledge gap for the winter is something that a lot of us are really, really focused on right now. And there's a lot of opportunities. This seems like really basic stuff, but it's not out there. Hopefully by the end of the year, we'll get this paper in press, and then this will be out there. This is going to be the sort of the standard reference for winter stratification across the Great Lakes for some time now. I'm excited about that. So thank you very much.
So any question from the student? First? I think it was the graph that had the stratification between all four of the lakes. You said there was always a hump in Lake Superior.
Oh, yeah.
Is that, what's that caused by, / is that from the ice?
So you're talking about this?
Yeah.
This right here is that measure of stability, the strength of stratification. And the fact that they're always non-zero in the winter means they're always forming stratification. So, every, if I were to take this graph and instead of plotting it for those 3 years, plotted it for all, whatever, 18 years that I have data, every one of them would look like one of those. That's all I'm saying, that this curve is always non-zero. It's always forming stratification. Whereas at those other sites, especially Lake Michigan, it's basically zero, except for a little bit where it'll form stratification, then there will be a puff of wind that'll just quickly mix it away. So you don't get that robust stratification that you get in Superior and in some years in Huron, but not others. In the back.
Those three ones, are they approximately the same depth?
Great question.
Oh,
Yeah, I'm sorry. I'll repeat the question. So the first question just had to do with interpretation of the graph that's up right now. The second question was about depth of these three moorings. And we can't control for that, right? The moorings are where they are. So Superior, 185, Michigan, 150, and Huron, a little over 200. So they're not factor of two different, 150 to 200 meters with Superior sitting in between. And I think that those differences in depth are going to play a role in understanding. One thing that, maybe I said this, but one thing that I find really fascinating is if you look at the range of heat content in Superior and Michigan, they're both small. Huron has this huge range. And I think it might simply be that there's more water there for it to cool down. So there's another one here.
Yeah, is there an effort to fill in that data gap that exists in the northern part of Lake Michigan right now, or like get a second more in there? Or
yeah, so the question is about what is the Great Lakes community doing to fill in some of these data gaps, especially northern Michigan. I'm not aware of any activity on Michigan. This colleague of mine at Toronto has been piggybacking some temperature sensors on an acoustic array that people put out to study fish migration. I just started looking at that data last week, and I have a lot of suggestions for how they could do it. Because he's looking at the upper portion of the water column and neglecting the deep parts. Like, well, you don't learn about stratification unless you measure the whole water column really, really well. And again, it's just not that expensive to do. The boat that you have, the technician you hire, the students you pay are all a lot more expensive than a handful of temperature sensors. And so hopefully the work that Matt is doing on expanding into Ontario and Erie there's a huge acoustic array across the Great Lakes. And hopefully we'll be able to expand that work to a bunch of those other sites.
Any question from the Twin Cities?
Oh, they just posted something. Can I over it?
Yeah, you can read it.
Questions, do you think interannual climate variability modes are reflected in lake heat budgets? What observations do we need to find out? And so this is I guess I don't need to repeat the question. So do sort of global climate, um, interdecadal variability like ENSO or the PDO or something like that, do they play roles in setting these heat budgets? I think the answer is, if you have a system like, people are familiar with the idea of ENSO, El Nino, it's these weird oceanographic patterns in the tropical Pacific that happen to influence air temperatures across North America and other places. The PDO is the Pacific Decadal Oscillation, the AMO, Atlantic Meridional Oscillation. There's been a lot of work done trying to understand how variability, especially in ice cover, is related to those. And none of the work that I've seen I have found particularly convincing. People are doing these huge multiple regressions. And it's like, if you regress enough stuff, eventually you will explain all the variability. But I've never seen anything that I look at and go, oh, clearly, when the ENSO index is high, we're going to have high air temperatures and we're going to have very little ice, relatively high heat. I have not seen that connection made in a convincing fashion so far. But I've certainly seen people try to make that connection in the past, yes. Anything else?
Any questions?
Oh, somebody just said something. You expect any change in pattern climate? Yes, absolutely, 100%. So I've done a bunch of work. We don't have water column temperature data back before anything that I've shown here. The handful of papers that I showed you where some data was collected, that data is as good as lost. It exists in that paper, but all the people who wrote those papers are dead by now. And the data was probably on an 8-track cassette or something like that. That's irrecoverable. And so we have to work with what we have. We do see very strong reductions in ice cover. We have ice records going back through the early 70s. And there's a lot less ice in the Great Lakes now than there was 30 or 40 years ago. There are a set of meteorological buoys that get deployed in the Great Lakes that started in about 1980. And so we have, whatever that is, 45 years of data from those at this stage. Those also show a really dramatic increase in summer water temperatures, which we happen to know is related in some sense to what happened the previous winter. And so, yes, not only do we expect these things to change, but from other observations, we know that the Great Lakes are responding to climate change. All of it's driven by air temperature, and air temperature is sort of the coin of the realm when it comes to global climate change. And so, yeah, the lakes are responding for certain. For these data sets that, Gloro goes back to the 90s, I go back to the mid 2000s, that's not enough data to say anything reliably about climate change. Just too short. There's so much interannual variability that we need really long time series before we can reliably, start to say something about change. One more.
Don't there's a correlation with, I guess, kind of like the pressure reduction of a lake and maybe wind direction varying throughout the winter? Like a north wind on Michigan would affect or on Erie or something.
Yeah, so the question has to do with fetch. And fetch is basically the distance over which wind blows. And so if this is the land and this is the lake, the fetch increases as you move away from shore. And if the wind is blowing offshore, you might expect things to be more and more developed the further offshore you get. I think the quick answer is that adjustment phase is on the order of several kilometers. And these lakes are many, hundreds of kilometers across. So there are going to be coastal regions where the fact that the wind was blowing offshore means that the response is going to be different. But once you're a few kilometers offshore, it's all the same stuff. On a smaller lake, that might be really, really important. But on these big lakes, and the fact that the wind is blowing from different directions, depending on the character of the storm that's blowing through, I don't think that's playing a huge role. If you look at our site in Superior, I don't have a piece of paper in front of me. The joke that Bob Sterner makes is that if you're holding a piece of paper, that has about the same aspect ratio as Lake Superior. the sort of thickness to width. These are very, very large lakes, even though they're deep. Their horizontal scales are just tremendous. So I'm gonna guess that doesn't play as big a very big role. Okay, great.
All right.
Thank you very much. And hopefully that's helpful for people in 5010 right now who are reading about this stuff right now. So whoever wrote me the question earlier, I'm happy to talk after this. So thank you very much.